Well, my name's Kevin Osborne. I'm a director of software development here at Overland Storage, and I guess I get all the questions. So I'm looking forward to that. So the idea here is we're going to pull back the curtain a little bit, try to get into some details from the questions you've already asked so far and some of the information Jeremy's already covered. Some of the slides I might go through kind of quickly because it's obvious you guys already understand a lot of this, but just slow me down if I go through some of them too quickly. I want to save some room for some of the deeper questions you guys are already asking.
Yeah. Note, you're not even the first scale-out vendor we've talked to this week. So yeah. The basic idea of scale-out is not new to us.
Right. OK, well, first of all, I'm going to just briefly touch on this slide here. I don't think we really talked about the network configuration of the back-end storage versus the front-end storage. The back-end storage, we have 4 ports on every node. And so what we do with the back-end storage is we set up a failover configuration by default. But you can change that to various forms of bonding depending on the type of performance you might need. So it's a failover redundancy trade-off versus performance trade-off on the backside. So you have some options there. And on the front end, we have 2 ports as well, which could be configured in a number of different bonding configurations. Again, depending on your network.
So they're dedicated front-end and back-end networks? And if I use 10 gig, I need 4 10 gig ports? Or do you channelize it?
Ports on the back and 2 1 gigs on the front if you want. Or else you can go all 1 gig or you can go all 10 gig. So those are your 3 choices.
OK, but you don't channelize the 10 gig and let me use 2 10 gig ports, 5 gig from each for front and back?
No. So the thing I want to point out, though, is about the volumes. There were some questions earlier, and I think we got this resolved, but I just want to cover it again, is that as far as the SnapScale is concerned, there's one giant volume, right? And all the peer sets and all these drives that participate in the peer sets, they all get contributed into this main volume. They're all just storage space for the volume, right? And then inside that volume, we can create logical volumes inside of that, which we call sometimes virtual volumes, that define sort of a view into that space, if you will. So I can create a volume for sales, another one for marketing, another one for engineering that's much bigger, right? But anyway, they all see the same. They all see the same space actually. And if I wanted to make sales get less space, then I could go in and actually assign a quota for that volume and restrict the sales portion.
Okay, so volumes exist for quotas and to define the realm of a snapshot?
Not the realm for a snapshot. It's really the realm of the view of the attachment. So you attach into that volume with a SharePoint or a mount point, and then that's your view of the world. Right?
So what's the realm? How do we define the realm of the snapshot?
The realm of the snapshot is the entire cluster.
So I have to
snapshot is a whole cluster?
Yeah.
I have to snap everything?
Yeah.
Okay.
So I think we already touched on the way the clients actually connect into the cluster. They're going to get an IP address for one of the nodes. The way they do that is through round-robin DNS. They just access the name of the cluster, and then round-robin DNS is going to give them the IP address for the next node in turn. This distributes the connection to the different nodes in the cluster, and hopefully, in the same time, will distribute the load as well.
So how do we handle multipathing?
So let's talk about multipath in a few minutes.
Okay.
So how do you handle if the data is not in that node? If the peer sets for the data are not?
Each node has exactly the same view of the data as any other node. So
it doesn't have exactly the same peer sets.
That's correct.
So the data may actually reside on a different node.
Yes. Let me see here. Spare drives. We're not going to talk about that here. We've already talked about peer sets. I've got a slide that's going to cover that in just a second. So I'm going to skip over this because we've talked about peer sets quite a bit. We're going to talk a little bit more about it as well.
We're going to have to talk about the sharding some more, but go ahead.
All right. And we talked about this redundancy, and now we can get to, already talked about volumes because you guys have been asking all the questions already. This is the slide I want to get to. So this is actually the way the access to the cluster is implemented. So each node fulfills 2 different roles. One role is the access point into the cluster, and that controls the security, the share list, and things like that. It also controls which protocols can access the cluster. The other role that it plays is part of the storage component for the cluster. It has hard drives in that node that participate in the storage for the cluster. You've got to separate the two, right? So access comes into the cluster through the node. The security is confirmed. The file request comes in. Now we've got to go into the actual cluster itself to find the file. And this is how it's done. We're running a variant of Linux in our box. It's probably no big surprise to you guys, right? When the file request comes through the SMB layer, it pops out at the VFS layer in Linux. That's where we pick it up with our gateway redirector driver. Our gateway driver picks that up, takes that file request, reformats it into a SnapScale RPC call. From that request, it can actually tell which peer set to talk to find the data or find the metadata. And I'll tell you a little bit more about how that works in just a minute. So then it issues a direct request to the peer set that it needs to talk to. And it knows which node to talk to in order to get to those peer sets.
Okay, if that peer set is not local, is that request across the front end network or the back end network?
The back end network, strictly the back end. Right. And the larger your cluster, the more likely the data is not.
As far as mapping, I'm not sure if it's the correct term, but the data address to a peer set is done through a globally normalized table across all the nodes?
That's right. It's a hash table.
A hash table.
Right. And that is a perfect segue into the next slide. Yeah. Right. So the way it works is if you're looking for the metadata, you look at the parent path for the object that you're trying to access, and you do a hash on that, and that resolves to a peer set number. So that tells you which peer set that you actually have to access in order to get at that data.
Okay, run that by me again.
They use the directory to do the hash to find a peer set.
You use the parent directory path to do the hash.
Okay.
Okay.
So the triple or dual redundancy is a node, it's a cluster-wide attribute.
That's right.
Okay.
You've got to think about the peer sets as a building block for storage, right? The more peer sets you have, the more storage you have. It's like, you can kind of view it like a giant hard disk.
Okay, but if the peer set member is chosen based on the hash of the parent path,
right,
then all of the files within that folder have to be stored in the same peer set.
Yes.
Well, that has performance and scalability problems, because now all of those files are on 3 drives, and I could read from all 3 of them in parallel, but if I'm writing, my write performance is going to be limited to 1 drive.
The files are not there. The metadata is there.
Okay.
Right?
Fine.
The files could be somewhere else, and that actually gets to a point later on down in the bottom half of the slide.
Okay, so we're still in metadata.
Yeah.
Okay.
Yeah. So when it comes to the data is decided where it belongs based on a couple of different items that we consider. One is making sure that the data is evenly distributed across the cluster. And the second item is making sure that there aren't any overly empty disks, right? So the disks with more free space are going to get chosen over disks that are fuller.
Right.
So there's a couple of different heuristics in there, but it's all kind of merged
It's
together.
not a hash based, it's more
this is more capacity based.
Rule based, kind of deciding where to put things and stuff.
Right. And then since I don't have a slide specifically talking about the shards, as you put it, this is probably a good place for us to discuss that a little bit more.
Okay.
So when the file is actually put down onto the peer sets, it's actually striped across them. So we just round robin across in the default for this release on 4.0 is 8 peer sets. And so we'll just go around those 8 peer sets and write the next block to the next peer set, or read the next block from the next peer set.
Okay. So, and how big's the shard?
512K.
Oh, okay.
So the SnapScale gateway driver is an intelligent driver. It knows where the data is. So if we look at directory lookups, as we kind of already talked about, we look at the path, and then that tells us which peer set to go and actually get the metadata for that directory. So in this case, the northwest ends up on the blue peer set, the northeast goes on the green, and et cetera. They could actually hash to the same peer set or different ones. Different paths are going to hash to different peer sets. The real challenge here becomes when, oh yeah, one other point which you already made, Howard, which is the metadata for a directory is all going to be on one peer set.
Right.
The challenge here comes when you start adding more peer sets, because now your hash table has changed. And so when that happens, we do have to do a re-indexing. And what you'll see when you add a couple of nodes to your cluster, or you add any more peer sets to your cluster, we're going to go in the background and we're going to say, oh, you've got more peer sets. That means I can spread my directory structures out more across the hash. That means I need to do a new hash table. I have an old hash table and I have a new hash table, and I have to migrate these small metadata files from their old location to the new location. This is what we call re-indexing, and it'll happen in the background while you're using the cluster after you've added nodes. It doesn't really seem to impact performance at all. It's just some shuffling. We have a series of locking schemes in place to protect the metadata as we do the move. So let's look a little bit deeper about metadata and how it's updated and how it's kept safe. And then we'll look a little bit more about the data. All right? So for the metadata, we have something called a primary peer set member, and then we have secondary peer set members. We either have one or we have two secondary peer set members. So the primary peer set member is the one who's in charge of making sure that all the metadata changes come through properly and get committed. Right? So when you create a file, that create request goes to the primary peer set member of the metadata server. And then that peer set member talks to the secondaries and tells them what to do. Right? And when they've committed the information, they confirm back to the primary, and the primary then can confirm back to the real client back across the wire that the create is done. A little bit serialized, but this way you make sure that all the members have exactly the right metadata before you move on. Metadata is crucial there.
So what happens if the primary disk in the peer set fails, if it hasn't updated the secondary member?
So if the primary has started the process and it fails, you've got to think this through. There's a lot of different failure scenarios that I'll covered here. So if the client has requested and tried to do the create, and the primary fails before it completes, the client will have to do a retry. Right? So the failure mechanism when the primary fails is that the secondary will then take over.
Yeah, but if there's data on the primary disk that hasn't been replicated to the secondary disk,
then it hasn't confirmed back to the client that the command has gone through. Right?
Yeah,
so the client's going to retry.
yeah, okay, yeah.
Right? So within a couple
the
seconds.
acknowledge will only happen after the secondary member has been updated.
Right.
Okay.
Right. Exactly.
And so not only is the peer set mirrored data across multiple drives, but you have multiple peer sets that can that can contain the metadata as well. In fact, there is multiple peer sets that contain the metadata, 2 or 3.
So remember that the metadata for a file, metadata for a directory
Small stuff.
is small stuff, and it's just on a single peer set. The metadata is on a single peer set. The actual data for the file is actually striped across multiple peer sets. So you got to separate the metadata from the data.
I thought you said the metadata had primary and secondary copies.
Ah, oh, okay, I see the
I assumed that was across different peer sets, right?
No, that's primary and secondary within the different roles of the different peer set members themselves.
Within the same peer set, different
Yes.
members. Oh, okay.
Yeah, sorry, I probably didn't make that clear.
All right.
Yeah, because a peer set is a mirrored pair or a triple mirror.
No, I understand, but I
But there's always got to be one in
charge.
charge, right?
Again,
And if that one in charge
For
actually
any given transaction, yeah.
Yeah. So we've got one that's for the primary, and the other ones are secondaries. And if the primary goes down, there's an election that happens between the secondary. Well, if there's only one secondary, he becomes primary. That's easy. But if there's two, then there's an election process that goes on to elect the next primary.
Oh, okay. So a drive is primary for the entire peer set.
That's right.
Okay.
For the metadata.
Yeah. And it doesn't really play much of a role with regard to the data. Primary doesn't really have much of a role with that.
What happens if I need to manage millions and millions of very small files? scalability problem at some point.
Well, I think that our file system is similar to many other file systems in that, if you pile up millions and millions of files inside of a single directory, things start to slow down. So if you distribute the files across a directory tree, it's really no difference to us from having large files or small
How
files.
many millions of files do you support in a single directory in a single file system?
Yeah, I think that we have to do some more testing on that to give the exact number, but it depends. I think it's in the thousands, not in the millions, for files in a directory.
Thousands.
Yeah, somewhere around 100,000 files in a directory. Things start to slow down a little bit at that point.
Yeah, at that point, just the fact that you're reading and writing starts to bottleneck.
Oh, yeah.
Yeah,
But
but many file systems have the same problem. I mean, if that's the type of application you want, then you'll probably be looking for a particular type of file
If
system.
you look at the scale-out system,
Yeah.
it means that you need to store a lot of data. So
yeah, but it's only a problem if it's that many files in one folder, because the next folder's metadata is going to be in a different peer.
like Amazon and Google, I think they should have
Yeah, so
2 million files.
it's a problem with excessive flatness.
Yeah.
And if you are that flat, you probably want to be looking at an object store anyway.
Right. Exactly. So when you actually try to find a file and read the file, for instance, you're going to do the lookup on the metadata as usual. And once you get the metadata actually has the peer set number for the where the file lives, on which peer sets it lives on. Remember, it's striped across them, so it has a list of peer sets that it's striped across. And the gateway driver takes care of all that. So what about data writes? How do we validate that the write makes it to all the media properly? So when we do a write, we don't want to do that serially, right? We don't want to write to the primary and then wait for it to finish and write to the secondary. So we do asynchronous writes to all the members, and so it's done in parallel.
And how many acts do you have to get before you act to the client?
Good question. Right. So what happens is that the first one to reply knows how many members are in that peer set. The gateway driver knows how many members are supposed to be in that peer set, but it doesn't know how many are actually there because one could have failed in the middle of the request, right? And the peer set actually knows its current state because it's talking to each other. The members are talking to each other all the time. So when the first peer set member that happens to be able to reply, it replies back and says, you should be expecting 2 replies, or you should be expecting 3 replies before you're done. And so then the gateway driver waits for that, for all the replies to come back before he moves on.
Oh, okay, so if it's a triple mirror, I got to get he's going to get all 3 acts.
That's right.
Okay,
So all 3 writes are done out in parallel, but then he has to wait for the 3 acts.
okay. So it's parallel synchronous.
Right. So the idea is it's 0 overhead replication, 0 overhead. There's never such a thing as 0 overhead, is there? But
No.
you get the idea.
There's no such thing as 0 overhead. There's no such thing as linearly scalable.
Right. There's no such thing as free lunch, right? Yeah.
Exactly.
Yeah. Okay, what about reads? How do reads work? The gateway driver uses multicast read. We don't use multicast for write because then that would fill the pipes on the other side of the wire with data that they don't necessarily need to process. But on reads, we can send out the read, it's multicast, to all the peer set members all at once. And then there's an algorithm to decide to arbitrate. There's no arbitration, actually. It's pre-decided which peer set member is going to respond. Right? So really just one of them needs to respond. However, if that peer set member is a little too busy with other requests, and it doesn't respond quickly enough, the gateway driver does a retry. If it does a retry, then the other peer set member will automatically take over.
Okay, give me a second to get my head around this.
Okay.
So the gateway determines what block needs to be read.
Yes.
He multicasts that
Right.
to all of the members.
Right.
The members, based on some hash of the request of some type,
Yes.
details unimportant,
Right.
know A, B, and C all got the request, and they all calculate the hash, and A goes, oh, wait, that means it's my turn to respond,
Yes.
and he responds.
Yeah.
And then if it times out, the gateway sends the same multicast again, going, but this is a retry.
Retry count has been bumped.
And then B and C go, oh, it's a retry, let's not wait for A, and they reply.
Yeah.
Okay.
All right?
Because when you first said multicast, I was worried that now you're pushing those IOPS to all 3 drives all the time. But, okay.
Yeah.
That's an elegant way to solve that problem.
You want a job?
Having called...
Yeah.
Yeah.
You've probably had that offer before. You understand it. Very good. So we talked already a little bit about the striping, the way the striping works. The key thing with this is, in the first release of our software, we put all the file data inside of one PeerSet member. And just as Howard pointed out earlier, we're restricted to spindle speed then, right? We've got one spindle that has to serve that file. Well, now in the 4.0 release, we actually stripe this out across multiple spindles, and that gives us the performance boost of having multiple spindles spin and send data all in parallel. It also allows us to distribute the data better, right? In the old days, in the earlier release, a big file would land, and that PeerSet would fill up pretty quickly.
Yeah, especially if it's like if that file is an iSCSI LUN,
right? Yeah.
Then good luck.
Exactly. So now that it's striped, that spreads the data out across as well. And the other thing that this does for us is it allows us to significantly increase our file size limitation. Before it was limited to the size of a disk drive, and now it's really, for practical purposes, it's kind of unlimited. It's limited to the number of PeerSets that you have participating in the drive stripe, in the file stripe. That's what it's limited to. So
the maximum file size is 8 times the drive size.
At this point, yeah, but that's configurable. We could change the number of PeerSets involved, and you can make it even bigger.
I'm not really worried that your maximum file size is 24 terabytes. That's
yeah. Yeah.
It's like, oh, okay.
Yeah, exactly. So for practical purposes. What was that?
Yeah, it's.
I missed that.
So the maximum size of a LUN as well as 24 terabytes then.
So yeah, this gets into iSCSI, and I don't have a slide specifically about iSCSI, so maybe we should talk about it here and now. The iSCSI striping is different from the regular file striping. We use more PeerSets for the iSCSI striping, so we don't have that. We wouldn't have that limit for iSCSI.
Okay, good point.
Okay, so iSCSI files are a special case that are sharded wider.
Yes, exactly.
Are you going to tell us how wide that is?
Right now it's 16 PeerSets, but again, it's configurable.
And when you say configurable, it's customer configurable or RAIN store OS configurable?
It's not in the GUI.
Yeah.
But it's it's a configuration setting that we could poke
potentially,
in.
yeah.
Yeah. So if you really need LUNs bigger than 48 terabytes, you call support and they dial in and go, here, let's tweak that for you.
Yeah, exactly. Right. So
but 48 terabytes is a pretty good size LUN.
Yeah. So before I move on from iSCSI, there were some other questions about iSCSI. I don't know if I've hit them all. Should we deal with iSCSI right now before we move on?
It'll come up.
Okay.
Multipath. That was the other.
Multipath. Right. Well, this is our first release with iSCSI. And for this release, for Multipath, we support Multipath through the same node. We don't support Multipath through multiple nodes. It's kind of...
So if a node fails, my LUN goes offline?
No. iSCSI we do support the failover of the LUN. The LUN, remember the LUN is stored on the volume itself, right?
Right.
But typically Multipath, from the way I understand it, really has to do with getting multiple, it started off with multiple network paths to the data, right?
Right.
So we support that through the multiple NICs on the front, on the client side on any one LUN, on any one node, right?
Right, but if my host is connected through multiple paths
To the same node.
Yeah.
And that node explodes,
Right.
then my host is connected to the rest of that volume through no paths.
Well, see, this is the thing. Actually your initiator is attached to an IP address. The IP address fails over to another node.
Okay.
And so now you still have access to your data.
Okay. So
But the data is on multiple nodes.
The data is on multiple nodes, but remember, all nodes can see all data.
right. So in the event.
Yeah, but there is back-end traffic to get from all those nodes to one node that is showing it to the host.
That's correct.
Okay.
Yeah.
So is it one IP address per
For LUN.
LUN?
Yeah. Or you can have multiple IP addresses, or I'm sorry, you can have multiple LUNs served by the same IP address, but each LUN is associated with an IP address.
A virtual IP address.
Yes, exactly. great questions. Good. I think I covered all those. Great, and this is, I just love this graphic, so I had to put it back in. Visualization's a good thing, right?
Yes.
So let's talk a little bit more detail about how the drive recovery happens, how the node recovery happens, and then the IP failover. I think there was a question earlier about IP failover, so we'll get a little bit more detail there. First, the drive redundancy. We're still read-write when we lose a drive on two-way replication, and we're still read-write when we lose two drives if we have rep by 3. So we still maintain read-write capability even though there's only one drive remaining in a peer set. If you lose the complete peer set, it's just like any other RAID system. When you lose enough of the members, the file system stops. But the nice part about our system is if you're able to bring back that peer set, but for some reason the second, third, fourth node turned off, you just turn it back on, our file system will be watching for that and can pick it back up and restart the file system.
So when you say file system in this context,
I'm talking about the volume as a whole.
the entire volume.
The entire cluster is one file system.
Yes.
Yeah.
Right.
So having two drives in a peer set fail, if it's a mirror, will bring down my entire cluster.
Yep.
Okay.
It's like any other RAID system or any other file system. If you take out enough pieces, eventually the...
Yeah, but sure, but your failure domain, if you're running like 20 boxes, is going to be immense.
Well, what are the chances of, you got to figure out the...
3 precise drives.
Yeah,
in one
it's a surgical
set,
strike.
Have to go out.
Very much, I mean, you could probably pull out, out of, say, a 10-node cluster, you could probably pull out 10 nodes, or 10 drives, rather, and chances are very slim that you would actually take out a peer set.
Well, sure, the chances are slim, but the impact is insane.
Yeah, it's like nuclear power plants. They don't fail very often, but when they do, they fail badly.
Right. Well, no one's saying that we don't need a backup, right? All right. So how does the rapid rebuild work? When a drive fails, the peer set announces, it does a heartbeat, and it recognizes the drive, one of its members has failed. It announces to the world that it's down one and it needs a new member. And the management software that runs on every single node, it's the same software on all nodes, they work together to nominate some drives that are out there, the spares. In order for a spare to be eligible, it has to fit a couple of criteria, and I think you already know some of these. Right? It has to be bigger than, larger than, or equal to the smallest member of the remaining drives in the peer set. So it's a typical mirror sort of arrangement.
Right. And if a 1 terabyte drive fails, 1 terabyte, 2 of those terabytes just get wasted.
Yes, and I'll talk about that in just a second. There's something we can do about that. Yeah. The other thing is it has to be a drive on a node where no other members of that peer set reside. Because remember, the whole idea of spreading these peer sets out across nodes is so that when you take out a node, you don't take out the entire peer set.
Yeah.
Right. So your question about you've lost your 1 terabyte. You can no longer buy 1 terabyte drives. You have to buy a 4 terabyte drive, and you put it in, and you've wasted 3 terabytes. So you put it in, it rebuilds, and you're right, it only uses 1 terabyte initially. After rebuilds, though, you can pull out that other 1 terabyte drive and push in a new 4 terabyte drive in place, and now you've got a 4 terabyte peer set. So we always format the drive for the full amount of space on the drive, but logically we'll only use the component of that drive that is needed for the peer set.
You encourage customers to pull drives out of an array? And how does the customer know which peer set he's pulling the drive from?
The GUI will show you. Yeah, the GUI will show you which one. But yeah,
Don't
we
pull
don't
the wrong
steer
one
people down
anyway.
that road. We
Imagine you'll
rather
pull
that they-
the wrong drive.
Yeah,
Again, if a single drive failure, a single extra drive failure
Yeah.
can bring down the whole cluster,
Yeah.
those two things combined feel very, very dangerous.
I'm exposing this to you guys because you guys are technical and understand how things work. We don't mention this in the documentation. So you're exactly right. in that-
Well, luckily it's on video, so it's not like it won't go out to the world at this point, right?
We'll keep it amongst ourselves.
Oh, thank you for that.
Yeah.
Yes.
You won't tell.
Right.
We won't tell anybody.
Oh, perfect.
YouTube will.
Hey, I signed a non-disclosure agreement with these guys years ago.
Luckily it's elapsed.
All right, so that's the growth thing. And so, all right, so the synchronization process. So now we've found a drive that works, and we need to build the data over from the remaining member of the peer set over on to the new member of the peer set. We actually use rsync for this.
Okay, so the shards look at least at a level that rsync can recognize like their files.
Yes.
Okay.
Yeah. And actually that goes back, I kind of skimmed over one of the earlier slides. The way the data is actually stored, you can kind of think of there's two file systems involved here. Rewind a little bit here. Right, so the data comes in through the client, from the client through the, through the protocol, comes in through the VFS layer. At that point, it goes out across the Snap the Snap RPC layer, goes out to the peer set members. And that's where our cluster file system really lives. So our cluster file system lives at that layer. And then it actually stores the shards and the various components in an XFS file system on the drive. So when it comes time to rebuild that drive, it's really pretty easy. We can just point rsync at the source and at the destination and say, go. Except for it's not that easy, is it? Because you're syncing the data over. And behind rsync, more data is arriving. And so what do you have to do when you get to the other end? You have to turn around and do it again, right? I liken it to the old software engineer joke. Software engineer gets stuck in a shower reading the shampoo bottle instructions, lather, rinse, repeat, right? And so you're just kind of stuck there for a long time, right?
So eventually you run out of shampoo.
Oh, that's good, yeah. Or hot water. So what
it's
happens?
An endless loop till the error condition.
Yeah. So in this case, what we do is, as you cycle around this loop, each time you do it, there's less data generally to process because the amount of data coming in that you have to pick up on the next pass is however much new data has appeared on this peer set and on this peer set only. So it tends to be a fairly small amount. After a couple passes, it's a very small amount. And we do another thing to optimize this. What we do is we keep a track of the actual files that have hit that volume that we're trying to synchronize. Since we have the file system above, we can actually track exactly which files are coming in. So we keep a list of which files have been modified, and when it comes time to come around again, the last time we lock the file system on that peer set as read-only, and we do a final synchronization. This final synchronization typically takes a second because there's very little data left to do. The client never experiences any issue, any interruption. And after that's complete, the member is officially part of the peer set. All right, so what happens when a node goes offline? Well, a node has a lot of peer set members, doesn't it? So when the node goes offline, a lot of peer sets go degraded. When all those peer sets go degraded, the system, each one of those peer sets argues over who gets to repair. Now, depending on how you provision your cluster, you may or may not have enough spares to repair an entire node failure. That's a choice you make when you set up your cluster. You can select how many spares you have. So if you have enough spares, then all those peer sets can repair. If you don't, then they're left and degraded. It's still functional. You're still serving files and everything, but you're in a degraded state and not as protected as you were before. So then the administrator needs to add a replacement node. Fix the node, however, whatever the issue is. They need to bring in a new node. So they bring in a new node. They add it to the cluster as soon as it comes in. All the drives in that node will become spares. And then all the previously degraded peer sets will rebuild. And thus, you're back up and running with your full redundancy again.
So, I mean, that's why you encourage people to use triple redundancy.
Right. Right. The other thing that happens when you lose a node, as has already been pointed out, is you lose your IP address. Right? Well, you don't lose your IP address. It's now going to be assigned to another node. And we use CTDB. I don't know if you guys are familiar with CTDB. Heard of that before? It's a open source product developed by the Samba team specifically for IP address failover as well as many other functionality. Much of it dovetails with Samba to provide cluster-wide security and things like that. But it handles IP address failover. So the way it does that is it senses the node failure. it knows that the node has gone down. It knows which IP address that node was servicing. It also has TCP connection information in a cluster-wide database handled by CTDB. So it then will say, all right, who can serve this IP address? The other nodes will then say, I can serve it. So a new node will get the IP address, and once it gets that IP address, it will send out a TCP reset on the connections. The client will then reset its TCP counters and et cetera, and continue on with its communication. So file-based protocols, such as SMB, FTP, NFS, they will not have to reconnect. They will not have to remount. They will not have to remap a drive letter.
So there's no PCIe SSD clash or any SSD support in the product. It's all spinning media. Is there DRAM caching in the product?
At this point, we're considering a couple different ways to do that. Not today, but we're thinking about a couple different ways to do that and where best to put it.
And so when a write comes in, it's got to go immediately to disk in the primary member and then be replicated to the secondary and third. Yeah.
There are a couple layers of caching involved in the operating system itself.
Yeah.
Obviously, we got quite a bit of RAM involved in the individual nodes.
Yeah,
so
you do.
So they'll cache in the Linux file system, as well as in our cluster file system itself. We have some read-ahead caching and some other caching that's built into that as well. So,
there's no real write caching anywhere in the system.
Not until it arrives on the peer set.
Excuse me.
Yeah.
I saw XFS somewhere in your slide.
Right.
As the internal file system that you use in a single node.
That's right.
Calculated node, and you need to run the FSCK.
FSCK.
Sorry, my English spelling. Because it can take days, potentially.
Well, remember, we can run without that node. You could take a node offline and you'd be in a degraded state while you were there, but you can run without that node.
So
you could do that.
Out a node for days to run the FSCK, and then you can.
There might be better approaches to protecting your data than going that route, but yeah, you could do that.
So how does, back to the question I had before, if I have a 3-node X2 configuration and I add a 4th node, how do you redistribute the peer sets to take advantage of the next node?
So there's a scheme that we have it's called spare rebalancer that I think we touched on earlier. And so basically what happens is when that new node comes in, they're all spares. And so what we have to do is find a way to move those spares and distribute them on other nodes. And as we do that, we'll actually find that we can form new peer sets. It's a little bit, I'm going to do a little hand waving here, but I think you'll get my idea. Yeah, apparently.
So, but effectively, the new 12 drives will ultimately introduce 12 new spares to the cluster?
Initially, yes.
Initially, okay.
Yes. So at that point, you can decide, well, am I adding 1 node or am I adding 2 nodes? If you're adding 2 nodes, they'll both come in together.
Then you're adding
got rep
24
by 2,
spares. Yeah.
You got 24 spares. If you've got rep by 2, they're going to form peer sets, and everything's going to be good.
If you rep by 2.
Yeah. If you rep by 3 and you add 3 nodes, again, everything's good. If you don't want to buy that many nodes, there's another route. And so what you do is you put in however many nodes you want to buy that I assume is less than your replication count. Yeah. Right? And immediately it's going to, from its spares, it's going to form peer sets with whatever spares are left on your cluster. And then you're going to say, redistribute the spares. There's a couple of heuristics that come in here. One is you've configured your cluster with your preferred number of spares. All right? This is how I would like to run. I would like to always have 4 or 5 spares in my cluster. So you just establish that in the GUI as a rule.
And that's an absolute, not a relative number?
It's an absolute in the sense that if the cluster can achieve that, it will.
Okay, but I can't
If it
say
needs
I
them in
always
order
want.
to rebuild, it will use them in order to rebuild.
Right, but I
You'll
can't
never
say
exceed that.
I can't say I want 3% spares.
No, we use numbers.
Okay. So if
anyway,
I really am growing this thing
Let's say you had this
substantially,
configuration and you said 5 spares and you already had a triplet environment with 3 X2s and you added the 4th X2. Now you have 5 plus 12, you've got 17 spares.
Right. So what we do is we actually will take the rep by 3 and knock it down to rep by 2, rebuild onto one of these other drives, and make that drive that we just took out be the new spare. So now we've taken the peer set and spanned it across to the new node.
I'm sorry, go over that again slowly. You take the rep by 3 and you decrease it to rep by 2 for the cluster?
No. For that,
some
we take
peer
a
set.
peer set and we say we degrade one member and
Okay.
rebuild onto the new system.
and until the rebuild is over, your protection level has decreased.
Right.
So does that mean that if I was in a X by 2, that I only have one active drive while this rebuild is taking place?
That's right.
Of multiple terabytes being transferred
That's
over
why
the
we
1
recommend
gigabit?
you
X
add
by
2
3.
nodes instead of adding 1 node at a time.
Okie dokie.
So let's see, I covered the IP address failover. Great. The last thing I want to talk about, and my last topic here is...
Oh, good, because we're starting to run short on time.
Yeah. Is the configuration information. And each node, as I mentioned before, each node represents the security layer, or the access point to the cluster. So each node has to behave exactly the same. And so this configuration information has to be exactly the same on every single node. So we have a cluster database, clusterized database that we've devised that replicates this information across all of the nodes. And so when a new setting comes in through the GUI, that setting is map reduced out to the nodes. They all receive it. They all update their cluster database. What happens if one of them misses one of those requests and doesn't get the request for some reason, right? Some network collision or something. Well, every 70 seconds, they send out what's called a merge packet, which says, this is who I am, and this is my state of my cluster database. And in that state information is really it has a version number of each of its fields. And so if it discovers that it's down rev on one of its fields, it will then proactively get that field updated. So it's kind of a two-way update. We map reduce the information out to the nodes, and then the nodes themselves are also looking to make sure that they are up to date as well. The other nice part about the configuration database is that it's like a rubber stamp, right? Once you have that configuration database on the node, it's like now you're a member of the board. You know, you've been assimilated. You are like everybody else in that cluster, right? So the beautiful thing is that when we add a new node, it's relatively easy to initialize the new node. We just copy the cluster database over onto there. It iterates through that cluster database, makes all those settings, and ta-da! It's now assimilated. It's now part of the cluster.
So what happens if 2 nodes miss an update?
Well, each one is monitoring on their own, right? The user interface, the node, whichever node the user interface is running on, it always updates itself first, right? So it'll have a newer version on it. As soon as one of the nodes has a newer version, then all the other nodes will find out about it within the next minute.
Yep. Okay. So changes can only be implemented from a single node, which is running the interface.
Running the GUI,
Okay, yeah.
right.
Back to my question before, what do you consider the advantage of the peer sets versus something like the more normal, either mirrored or RAID kind of protection kind of thing? Why'd you go down this path?
Well, it's an object store architecture. The idea is that
I've talked to a number of object storage vendors in my lifetime here.
Yeah.
And it's the first time I've heard of a peer set kind of configuration like you're talking about. And the way this is managed.
not sure exactly
most
how to,
object stores that have mirroring, they would mirror the data to any of the devices. There's no direct relationship.
They would mirror an object, not mirror.
Yeah,
a
you're
drive.
mirroring an object, not a drive.
And that disk. And you know, I could see either mirroring objects or mirroring slices and say, you know, 100 gigabyte chunklet to use three parse
even larger
term.
SCSI
Chunklet?
Yeah, which is three parse term
Actually,
for their.
chunklet is a three-part term.
use a chunk,
But
only chunk.
yeah,
Chunklet sounds like a
because
Swanson dinner, you know.
because the problem with the peer sets is the rebuild. That you have hot spare drives, not hot spare space.
Yeah.
And so if if a drive fails, now, assuming I'm doing X3, because in your environment I wouldn't do X2 ever, never, no, not ever. That means that I'm sucking the data out of those two drives, making them really busy. And I'm writing it to one drive, making it really busy. And if my unit of mirroring was smaller, then that drive fails, and the first chunk comes from those two drives, and the next chunk comes from a different two drives, and they rebuild
spreading the rebuild
all of
activity
the
across
drives, and
multiple
it's a
drives.
much more distributed process, happens a lot faster, a lot less overhead.
And the addition of a node is relatively complex and fraught with
2 nodes.
risks. You know,
Well, it's just that,
Well, no, not
you know,
really.
and then that the
unless you're
redundancy
adding 3
level is
nodes or 2
reduced
nodes,
while
whatever,
you're adding
depending on
capacity.
redundancy.
Well, remember, you can add storage in a number of different ways. You can add drives if you haven't fully populated to start off with. That will create new peer sets as well. So you've got what we call our scale up, scale out approach.
So if you add a drive, you do much the same thing. You'd select a peer set, you'd mark one of the drives dead.
No. If you're adding drives, so say you start off with the X4 and you only put 12 drives per node, right? So you get 24 empty slots on each one of those guys. Say you buy 12 more drives. You put 4 drives into each one of those.
Then you're fine.
And that's 4 new peer sets.
Yeah.
Right. And then the GUI will say, I see new drives. Would you like to incorporate them? Boom,
Yeah.
hit it.
But
It
if I
creates new peer
add
sets.
a single drive to that configuration,
It'll probably
how much
come in
the
just as a spare.
Yeah. Well, if you've got a 5-drive spare cluster and you're adding a 6th drive, then it's going to try to find some way of adding. It can't.
Not if you've got rep by 3, it won't be able to.
it can't do it.
If you've got rep by 2, it
Yeah,
Might
be able to.
although
Well,
you know, if
yeah.
I'm already in a scale-out architecture like this, the odds of my expanding in units that small
By a drive is
Yeah.
probably pretty
is probably
rare.
pretty low. But
Right.
But a node,
yeah, oh no, clearly a node. You know, it's just there's a lot of this architecture because the mirroring is
fixed.
well, it's so
the
granular.
drive,
The
though.
granules are so large. It's 3 terabytes at a time.
Yeah.
There's a lot of data movement that has to happen.
Yeah.
And if the granularity was finer, then there would be a lot less data movement that has to happen whenever any event happened.
Right.
And it would also let you spread all of it would let you wide stripe wider.
Interesting.
I mean,
All right.
I understand the concept. It's like
yeah.
somebody had RAID on their mind and said, how do we distribute this RAID, and didn't look at the more modern sub-drive RAID mechanisms and go, why don't I try and distribute that?
Okay. Well, thank you. And I'm going to turn it back over to Jeremy, who's going to do a quick
Quick wrap up.